Okay, everybody, today we're going to talk about internal forces. So, if you have a balloon and you are stepping on the balloon, then if we diagram that with the free body diagram, we have a foot down and a normal force coming up, and if we say it's static, then the forces cancel, and therefore the balloon doesn't fall, right? Wrong! Because there are internal forces. Acting on the balloon. And internal forces do not cancel out. Because if you have a box that's being pushed in this direction and you stop it by pushing in this direction, but this force stays, this thing is going to get squeezed. So, this happens for things that aren't as rubbery as balloons, like, say, everything in the universe. And it's our job as mechanical engineers or aerospace engineers or whatever engineers or whoever you want to figure out what these internal forces are. Because internal forces lead to failures. And by failures, I mean breaks. When your product breaks, you get fired. Or breaks in an unexpected way, right? So there are a few conventions to remember when going over these internal forces. For example, the sign conventions that all engineers use. So for shear force, both are axial forces. So for axial or normal forces, you've already seen this in trusses. Tension is the same as positive. That looks like this. Compression is negative. So, if you want a mnemonic device, a memory thing, you can see these arrow pointing as little greater than or lesser than figures, but the number in between and zeros on the end. Which is positive number and a negative number. That's a helpful little mnemonic device. Okay, then we have the shear forces. And basically a shear is like when you're ripping a piece of paper. You got forces going two different ways and a rip in the middle. And you tend to have them sticking out of ends of things. So, if you're looking at the right foot, you need to find a positive shear force going like this. Now, when you're doing your sum of the forces in the x and y, this is still negative, but this is what we consider a positive shear force. And you're looking at the left foot, and then positive goes up. Let me see if I can say it find a reason why textbook with me. Shear force that causes clockwise rotation, so this is going to go woo with a real force. It's not. Is positive, and if it becomes, so actually this is also positive because they're both causing clockwise. So, that's nice. Alright, bending moments. Here we have the right foot. Wait, no, this is the left foot. And here's a right foot. And if the arrow is pointing up, regardless of the way it's turning, if it's pointing up, it's positive. There is no particular reason for this. This is just what we, as engineers, have decided. So, for this, the mnemonic device, if it's pointing up, it's positive. Shear force, if it's turning it clockwise, it's positive. These go against all things you've ever thought about, but it's how we do. Let's do an example. Alright. So we got a crazy example for us to do. We have this wall, and we have this beam, and there's a pin joint connecting it to another beam, and there's a slot joint. So that's like a slot and a pin, and then there's a wall. In addition, we have this point moment applied of 350 pounds force. From here to here, we have a ramp function distributed force that goes from 0 to 80 pounds per foot. And then we have a 500-pound force here, same point, that makes a 60 angle. And those are our forces and moments being applied. We're going to call this point A, this point B, this point C, and this point D. And we're also going to look at the shear and normal and bending, shear and normal forces and the bending moments at this point E and this point F. And our distances are 2 feet, 1 foot, 2 feet, 3 feet, 2 feet, 4 feet, and another 2 feet. for a sum total of 2, 4, 6, 8, 12, 15, 16 feet. And we want to know shear at E, normal force at E, moment at E, shear force at F, the normal force at F, and the moment at F. So, step 1, three-body diagrams. Now, an important thing to notice is that we have three bodies, because they're connected by these joints and by these walls. Therefore, we're going to need three free-body diagrams. So, we're going to have one from A to B. Alright, and this is going to have, at A reaction moment, vertical reaction force, followed by one, and a horizontal reaction force. And at B, we're going to have, because of the pin joint, we're going to have a vertical reaction force and a horizontal reaction force. Oops, the X and matching Y. But no reaction moment because it's pin joint. And we also have this applied moment. And then for the C, we have, this is reaction forces we have. Now, it's the same reaction force here and here, so we need to keep the same direction. So if this force is pulling, going this way, then it's pulling on this one. So this one also goes like this. And if this one is being pushed up, this one will be pushed down. So it'll go like this. And then we have a Y reaction force at C. Because it's a roller joint, it's not going to stop it in the X direction until we get to the end of the roller. And we're going to assume that it doesn't get to the end of the roller. And then we have our applied forces. We have 0 to 80 foot. And I'm going to divide this next one up. Components, the 500-pound force at 600 degrees. No, I'll just leave that as. And then finally we have CD, which has again, keeping with making our signs or directions of our arrows match. Or not necessarily match, but make real world sense. And then reaction force at D in the Y direction, reaction force in the X direction, and the reaction force. Okay. So we want to solve for these points E and these points F. And what you notice in both of these, both of them are these unknowns that can be solved for here. So we are going to solve BC first. Alright, let me pull up the sheet. I'm going to redraw BC. and we're going to do new. So, sum of the forces in the x is equal to 0. So, P in the x direction is plus 500 pounds. Wait, those are in the negative direction. Sum of the forces in the x equals 0 minus the x minus 500 pounds cosine 60 degrees equals 0. So V sub x equals negative 250 pounds. This is 100. Where was it? Oh yeah. So what this negative means is we picked the wrong direction. That's okay, we can fix it later. So then we're going to do a sum of the moments about point B equals 0. That is B. So we have, for this distributed load, we have an equivalent force at its center of this thing. So the equivalent force is basically the area of this, if you take this to be the height. So that's 80 pounds per foot times 3 feet times 1 half is equal to 120 pounds. And its location is at 2/3 the length, which equals 2 feet. So, what did I say? Okay. So we have the moments about B, and this is going to cause it to rotate clockwise, so it's minus 120 pounds times 2 feet minus 500 pounds. We want the perpendicular one, so it's sine of 60 degrees, which is the square root of 3 over 2, times the distance, which is 3 feet, plus reaction force at C times that distance, which is 5 feet. And that's all equal to 0. We do some algebra, and we find that C sub y equals 307.8 pounds. Now, if we do the sum of the forces in the y direction, we have okay, C sub y minus B sub y minus 120 pounds minus 500 minus 60 pounds equals 0. 500 times 60 degrees pounds equals 0, which is C sub y equals 553.0 plus B sub y. And since C sub y equals 307.8, so B sub y which is 307.8 minus 553.0, B sub y equals negative 245.2. Hooray! Pounds. So now we have our 3 numbers that we wanted. We can go back and do the other first. So I'm going to do E first, because it comes first in the alphabet. So we're going to redraw that. So if you remember, we got our directions wrong here because it both came out negative to B. So that means we have to change our directions on this free body diagram. So it's going to go E, S, C. 250 pounds, and y equals 245.2 pounds, and then we have a in the y direction, a in the x direction, and moment about a, and then a 350 pound moment, and then point E. And we're going to make this nice cut here, which is going to give us two sections to look at. And we have no unknowns on this side. Well, we're going to have unknowns for our internal forces, but no external unknowns. So we're just going to look at this left, this part. So cut, and this, and we have our external forces. Normal force, shear force, bending moment. Alright, so we're going to do our Newtonian summing forces. X equals 0. So normal force of E equals 200 pounds of tension. Sum of the forces of the Y equals 0. E equals positive 245.2 pounds. And the sum of the moments about E equals 0, so M sub E must equal negative. Yeah. 245.2 times this length, which was 1 foot. Yeah, so negative 245.2 foot-pounds. Hooray! No, for the other one. So we have C sub Y equals 307.8 pounds. Yeah, and then we have C in the Y, C in the X, and the moment others. So then we make this cut. We go with the side we know about. And our sign convention, that, that. So that's yeah. Alright. NF is going to equal 0. BF is going to equal negative 307.8 pounds. And NF is going to equal positive. What's that? It's 4. Okay. It's going to equal 4 times 307.8. Which is 1231.2 foot-pounds. And thus we have solved our problem. Hooray! That wasn't so hard, was it?